STAT340 week 13. And this week we have no new topics really. And actually I find it little point in sort of repeating stuff in any detail, because the videos are out there, so you can just go back and see it for yourself, whatever you wanted to repeat, and the exercises and everything. So I will just try to make some sort of a summary here instead of what we have been through, and also look at some details. So what is this short lecture here? First, I will just briefly go over the different approaches we have seen during this course. Depending on how the data look like, we use different approaches, right? So just a brief summary of that. Then I will spend some time looking into this model equation formulation, and not that this is super important in this course, but it is of some importance to have this under your skin, because it enables you to read what other people write, right? So I got the impression during the assignments and stuff that this is something that many people feel is a little bit difficult. So I was thinking of looking a little bit into this, using from assignment 3 actually, the example. And then finally some concluding remarks, you could say, on how we can do data analysis in real life. Okay, explorative studies. That's where we started this course in February. And we have a data set, and the data sets we talk about in this course is always tables of data, right? So we can write them like this, where we have then P variables or columns. So the columns go from 1 up to P here. The second index is always the column index. And we have N data cases, the rows going from 1 down to N here, the first index. If you have a data table like this, you should always start by sort of plotting your data, I would say. That's the sensible thing to do. Try to get an overview of the data if you can. And plotting is probably the best way. There are some other summaries, right, that you can do, but if you can, you should plot your data. If you have just a few columns, that shouldn't be too difficult, right? We saw that if you have many columns, we can, for instance, use PCA that we focused a lot on here, or principal coordinate analysis as well, for compressing it so that you can actually plot it. Because if P is large, if you have 100 columns or even more, you can't plot them all. So compressing it down to Q dimensions, and for plotting it means Q equals 2 really. Okay, you can also plot 3, but in reality it's like 2. And then once you done this plotting, try to look for groups or gradients. Grouping you can see directly. If you make a score plot, you can see if the data cases group fall into groups, right? To see a gradient, you need some kind of extra information about your samples, so that you, for instance, can color them by this extra information. Otherwise, you can't see the gradients. But look for groups and gradients in a plot like this. We also talked about clustering, and I have a feeling this point here was not really emphasized when we talked about clustering. So clustering can also be used to sort of overlook your data, right? Instead of trying to project everything into 2 dimensions, so you can sort of look into the data space through a window of 2 dimensions like we do here. You can instead, if you have many dimensions, right, you always lose something by by compressing and projecting into 2 dimensions. An alternative is then clustering. Cluster the data into different regions, you could say. So each cluster becomes sort of a cube or a region in this space of data. And then you can start to investigate what is the difference between these cubes or regions, right? And again, look for groups or gradients. And the advantage here is, of course, you did no compression, right? So this is the original data space you are investigating. So this is something you can keep in mind. Clustering as a sort of a way of compressing data, but instead of compressing the number of dimensions, you compress it down to a fewer samples, you could say, or data cases. One representative for each group or cluster or cube. Okay, sometimes we also have a response variable, or not only sometimes, quite often actually. And I mean, if you want to do the coloring of the PCA plot or investigate the content of these clusters, you need this extra information of some kind, right? And then you, once you have such a extra supervising information, you can also do explorative PLS. We looked at that in one exercise, I think. I just mentioned it here because it's sort of an alternative to PCA then. So again, you compress or project into a lower dimension, but you use this information for finding the dimensions, right? Instead of PCA that doesn't use this extra information. So that's also an alternative here. But in most of this course, we haven't done exploratory. We have done modeling of data and specific testing and regression models. You use regression whenever you have a numerical response. So this is sort of quantitative, right? Quantitative. And numerical predictors. So the columns here are also quantitative. However, we may include factors, categorical variables among these, but they should not be, it should not be only factors, right? There must be some continuous variables here to call it a regression. And usually we have most most quantitative variables, but with only 1 or 2 factors, perhaps. We saw that analysis of covariance, we call it then, but it's actually regression. We saw also last week in the very last topic of this course, Poisson regression, as an alternative to the what we may call the Gaussian regression, right? With normal distributed residuals. If you have count variables, you typically don't have very normal distributed residuals. You have something which resembles a Poisson distribution instead. And whether you should use one or the other of these, inspect the residuals and make a decision. I mean, count data typically have this Poisson distribution, but I think that it's fair to say that the counts must be sort of low. I mean, if your data are counts but they are in thousands, then it's usually more like a normal distribution anyway. So the Poisson regression, I would say, has its big advantage when the counts are few, 0, 1, 2, 3, 4, right? Not like tens of thousands or whatever. I have a lot of data myself where the data are actually counts, but they are counts of reads from sequencing in bioinformatics. And these counts come in thousands or millions even, and then there is no point in using a Poisson regression anymore. So inspect the residuals for whether you should use one or the other here. Apart from that, it's fairly similar, right? ANOVA. So what is the difference? The response is still numerical, quantitative here, But now the predictors are factors only factors, categorical. And typically we don't have very many either, because this is typically designed experiments or intervention studies, right? So it's not like you go out and observe a lot of variables in nature. You design your experiment and you vary systematically a few factors, right? So P is pretty low typically when you do ANOVA. And each factor has then 2 or more levels, categories. And then we use ANOVA. But the response must still be numerical. Classification, well, the difference is that now the response is the categorical one. And the predictors are typically numerical, quantitative, even if we may include factors here as well. So it's sort of like regression, the X's, the difference is in the response. And we saw some methods for doing classification. And the logistic regression is the one that sort of comes closest to the regression approach, right? Even though we also saw some LDA and stuff. Model equations is something that people, I think, find a little bit difficult. So that's why I thought we should have a look at this then, as we look back at what we have done. So I started out with this assignment 3, because there you were given a model equation like this, right? And you were asked to sort of state a little bit about what these terms are. What are these different parts of this model equation, right? And the indexes are I, 1, 2, 3, well, J, 1, 2, 3, 4. You can actually interchange these two, right? I have now considered this to be the sort of treatment effect, right? With 3 levels, because that was what was in that data set. And this is the family effect. You can, of course, decide which Greek letter you use for which one of them. So you could have swapped this around without being wrong. And then we have K, 1, 2, 3, 4, which is the number of these boxes that the plants were grown in. And there are 4 boxes for each treatment family combination, right? So it's nested, that's this notation. So it's not really 4 boxes, it's 4 boxes per combination of these two, right? So it means it's actually 48 boxes when you see this notation here. And 5 plants then in each box at the end here. So what you should immediately notice is that the indexes you have on the last residual term here is always the same as you have on the response itself. That's the first thing you can sort of notice and make a rule. These other one may vary a lot, but the last one here and the first one here should have the same indexing. I can't think of a single case where this is not true. And of course there are 2 random terms here, stochastic terms, right? This one is random, normal distributed with some standard deviation here, no expected value, because all the sort of expected part of the response is described by these here, right? The Greek letters, they are sort of the fixed part, right? That adds or subtracts something. This is just variability. And also this one here, variability. With a different standard deviation. So there are 2 sources of variation, we can say, in these data, sort of random variation, because there are many sources of systematic variation. These are the ones here. Okay, so let's see how do we sort of write an equation like this? How do we sort of end here, right? And that is what I was thinking of elaborating a little bit around now. So what I would actually do when I face a data set like this, I would start with the very simplest model of them all, saying that the response that we observe is simply some expected value plus some randomness. And in this case then, notice the index I must then go from 1 to 240 because there are 240 observations. So all observations, all 240 of them, come from this sort of model, right? And if the world is like this, how should the data look like? Well, this is how I would then plot the data, right? Here we have the y-axis. And there is no x-axis here. I just collected the data points like in a swarm like this. And in this case then we have this mu value as the mean here, right? The mean value here is mu in our model. And then we remember this one is now just a normal distribution with zero expectancy and with some standard deviation. So it means that the variation around this mu now should be normal distributed. So if you sort of project all the points into the y-axis here and draw a histogram here, can you imagine you draw a lying histogram here? Then it should look like a normal distribution, right? When I look at the data, I get the feeling this is not really normal distributed because there are some points down here, right? Without being some points up here. It's sort of skewed downwards. And it looks like there are more points up here than down here, right? They're denser here. So it looks like this is not really normal distributed. But more important, we should now add, I mean, we have in this data set some additional columns of observations surrounding each of these 240 data cases. So what I would now do is to color these dots, for instance, by this treatment. And if we do that, exactly the same plot, but now we add colors because we know which observation comes from which treatment. And if this model now is the correct one, then the colors should now distribute randomly here. Because this is what this model says. It says that there is no effect of treatment. Everything beyond this single parameter, mu, everything else is random. But when we look at the plot here and how the colors distribute, we can see this is not random. This is not random. All the points down here are blue. All the points up here are green, right? These are the two different treatments, right? So obviously there is some effect of treatment here. It's not only randomness that explains this, the spread around this mu value. There is more systematic variation here. So that's why we now jump to the next model, where we now extend it by saying mu plus alpha I, where this is now the effect of treatments, right? So we have these 3 treatment levels, which is why I is now 1, 2, or 3, right? There are 3 levels of treatment: control, this is ME-J, and PIP-A treatments. And then we have some randomness, right? But notice now, this mu here and this E here are not identical to the ones we saw in the previous slide. They have the same sort of interpretation, but they are different quantities. Because this one no longer has exactly the same value as it had in the previous slide, and this one will no longer have the same standard deviation as it had in the previous slide, because we now added this term here. And of course J must now be 1 to 80 because it's still 240 observations. So since we have 3 here, I mean 3 times 80 is 240, right? So that's why J must now be 1 to 80. So the indexes also changes their meaning, right? I is no longer the same as in the previous slide. So how does the data look like now? Now we have an x-axis or a treatment axis here, right? Because we added this term. So now I can spread out the points according to the treatments, like this. So we have 3 data swarms now instead of 1. And we can clearly see that there is some sort of difference between the heights of this data swarm. First of all, the mu. What is this now? It's no longer the average of all the three, because we are now using this one of the treatments as reference, right? This contrast treatment, right? Which is default in R. Then mu is not the average of them all, but it's the average of the reference. So mu is no longer, doesn't have the same value as in the previous slide, because then it was the average of them all, right? In the previous slide, because then we did not split the three treatments. We considered everything to be one swarm. But now the mu means only the expected value for the reference, which is the control, the first level of treatment. And then we have alpha 2 is now how much the response changes when we move from the reference treatment to this treatment. Right? So you can think of it as how much do you have to sort of change the values of y when you move from this to this treatment. And the same for alpha 3, which is then when you go from the reference to this treatment. Right? You jump from this to over here, how much do the y values change? And notice there is no alpha 1, because when we have this reference, the treatment as one of the treatments as a reference, then alpha 1 is by definition 0, because now mu is the expected value at the reference, right? So alpha 1 is 0. There is no deviation from mu here, because mu is decided by this one. If we had this grand mean reference, it would be different, right? Because then mu would be the average of all, and then you will have also a value for alpha 1. But not in this case. So this is the picture now, right? And again, we should ask ourselves, is this now explaining all the variation in our data? Or is there some additional systematic variation that we are not really taking into account? And in order to see that, we can again color the plot because we have more columns, right? We have, for instance, this family column. And let me do that. Let's add this family information now as color to this plot. And then we can again see here that this is not really random. It should now be random within each swarm, right? Because we say that with this model, we say that, okay, the variation, there is a mu and there is an effect of treatment, but apart from that, everything is random. No, this is not random. You can see the green ones are typically the lower ones in all three swarms. These purple ones are higher values in all three swarms. There is some more systematic here. And we should also consider this family effect. So that's what we do now in the next model. We add also the family as a second factor here. So again, we have I1, 2, 3 here, the treatment effects. And now we add then the family effects here with 4 levels. There were 4 families. And then it means K is now 1 to 20. There are now 20 observations within each combination of treatment and family. And this should now again be 240 if you multiply them. 3 times 4 times 20. So how does it look like now? And then I decided to plot it like this, where we again have treatment on the sort of x-axis, but I split it into 4 panels. So the family effect is now by moving from one panel to another. And this is one way. You could have plotted it in a three-dimensional way as well, but I think this is easier to see and explain. So now we have a mu value here. And again, this is not exactly the same mu that we saw in the previous slide. And why not? Because remember, in the previous slide, the control dots were not only these, but it also were included these and these and these, because we did not separate between the families, right? So there were 80 control dots in the previous slide. Now it's only 20, because this is the control now, where we have so the reference, the control treatment and family A. These are the reference levels. So this is now the reference combination, we say, where you have the reference level of treatment and the reference level of family. The first level of treatment is control, and the first level of family is A here. So it's only 20 points left now for this reference. And mu is now the average of them. Or you can think of it as the expected value here. It's not strictly necessarily the average, but we will come to that. And then we have alpha 2 as the effect of moving from the reference treatment, control, to some other treatment. Right? How much do the y values change here? But notice, this is not only based on the difference between this swarm and this swarm, because it's equally important, the difference between this swarm and this swarm, because this is also the shift of treatment, right? But it's for a different family. But as long as we have a model with only main effects, notice there is no interaction term here. As long as we have only main effects, the effect of treatment is the same regardless of family, and vice versa. The effect of family is the same regardless of treatment. That's how main effects are sort of defined or behave, right? So the size of alpha 2 now is the average of the how much does it change when you go from here to here, and from here to here, and from here to here, and from here to here. The average of these four, that's the alpha 2 now. And notice this is exactly the same as it was in the previous slide. This is exactly the same as it was in the previous slide. So if you fit this model here and look at the estimates you get for the alphas, and then you go back and fit the previous model where you did not have this term at all, and look at the estimates you get for the alphas, you will see you get exactly the same estimate, down to the fourth value, the fourth digit after. Yeah, so exactly the same value actually, because we average, right? And alpha 3 is the same. How much does it change when you go from reference to this treatment? It goes down, right? And then from the reference to this treatment, again it goes down. Reference to this treatment, reference to this. So the average of these four drops, you could say, is alpha 3 now. How about the gammas? Well, we can draw it like this. Here we have now gamma 2. Because we take the mu from, we just copy it from over here, put it in the same panel here, and then we ask ourselves, how much does this swarm change compared to here, right? To the reference. This is the reference family, right? And then we move to a different family. And then we see gamma 2 is negative because it drops, right? So this drops to here. But again, this is not only based on these two swarms, because remember, main effects, the effect of this family is independent of treatment. So we have to also consider how much we drop from this swarm to this, right? And from this swarm to this. So it's sort of the average of these compared to the average of these. That's the gamma 2 main effect. When you move from family A to B, regardless of where you are among the treatments, how much does it change? And the same here then. No, sorry, yeah. So this one is now the expected value, you could say, of this swarm should now be mu plus alpha 2, since it's second treatment level, plus gamma 2, since it's in the second family level. Right? This should now be the expected value here, according to this model. Yeah, and we have of course the same effect of family C as gamma 3 and family D called gamma 4. And again, there is no gamma 1 because gamma 1 is up here, right? That's the effect of, that's described by mu. So gamma 1 is exactly 0, just like alpha 1 was exactly 0 when we have this first reference, first treatment, first factor level as reference. First factor level as reference. Okay, this one down here should now be mu plus alpha 3, since we are in the third treatment level, and gamma 4, since we are in the fourth family level. And this is now where we can sort of wonder, should we actually have some interaction terms here? Because I mean, this is the reason I highlighted this one, because it looks, this one to me looks like it could indicate we need some interaction. And why is that? Look at the, how if you compare this control swarm to the pip A swarm, in all the three other panels, we see that it drops here, right? It drops here and it drops here, approximately the same. But here it doesn't drop, or very little at least. So it means that there are some indications here now that, okay, the effect of treatment is not the same for all families. It's the same for the three first families, this effect of pip A treatment compared to the reference, right? It's approximately the same for the first three families, but not for the last. It looks like there's something other going on here. And if that is the case, we should now include the interaction terms between alpha and gamma here, because that's exactly what they do. They then try to modify, right? That means we would now get a positive interaction here, because we based on sort of the values of alpha 3 and gamma 4, we should now end up down here somewhere, perhaps, right? But we don't, so there is sort of an extra addition over here. So the interaction term for treatment alpha 3 gamma 4 would be, or alpha gamma 3 4 should be positive, yeah, something like that. I will not add the interaction term here now, and the only reason is because it will just leave us with more parameters, but it becomes extremely difficult to draw them in here because it's so many of them, right? But you can And it doesn't really change the picture, right? The plotting here will be more or less the same. It's just that there are more parameters to explain the differences between the various swarms. There will still be 12 swarms. So you can actually think about that yourself. What I wanted to do now is to again ask myself, is this model explaining all the variation, all the systematic variation? Is it now such that all the variation within each swarm is random? And again, we can color because we still have one column left to color with, and that's this box column. And that's exactly what I do here now. And now notice I only took out one of the panels now, and that is just for convenience. Just for convenience, because it's a messy plot if you try to plot them all, because there will be so many boxes, right? 48. So if we only look at the first panel, it's only 12 boxes, so it's more manageable to see the colors. And then we can actually see that this is not random at all. I mean, the plants that come from the same box, having the same color, are clearly different from the plants coming from other boxes, even within the same treatment and family, right? So we have now sort of tried to explain all the variants with treatment and family, but there's still some variation left here, which is systematic, namely which box the different plants were growing in. We can clearly see that. There is no mix of colors here, as it should be if this model was the correct one. So now it means we have to add the effect of box as well. And then in this particular case, you could say we decided to make that box effect a random effect. But of course we could have made it a fixed effect as well. I mean, this depends on other considerations than this. This just tells us there is an effect of box. But whether this should be a random or a fixed effect, we have to decide, and that's not the data itself that decides that, but how we consider box. If box is an effect that we want to study, or is it just some sort of noise that explains our data? And in this case, it's the latter. We think of box as just something random, but it's there, right? It's important to add it because it explains the variation in our data. So the fourth model then becomes this one, where we now add this effect of box as a random effect. So we again have the 3 treatments, the 4 families, and now we also have the 4 boxes, which is now nested inside each combination of treatment and family. So there are actually 48 boxes then, since there are 3 times 4, 12 combinations. And for each of the 12 combinations, there are 4 boxes. 12 times 4 is 48. And then we have finally L1, 2, 3, 4, 5, because that's the 5 different plants within each box, within each treatment and family combination. And that's all the data we have. 3 times 4 times 4 times 5 is 240. And then we can plot and see that indeed these boxes, if you color by the box, this is how it looks like. And now we don't have any more columns to color by, right? There could of course be that there are additional systematic variation here that we don't capture with this model, but that is now outside of our data set. But you should actually remember that, because it could be that you have missed some really important variable here, right? You have failed to measure it or observe it. So even if you use all your observed variables, it's no guarantee you have taken away all systematic or captured all systematic variation. But anyway, this is the way I like to sort of think when I build the model like this. Try to sort of have this image inside your head. I don't expect you to actually go and plot this in R, but try to have this image in your head. It's when you start with a simple model and you gradually extend it, right? Gradually extend it. And please remember that the parameters get different values depending on which other parameters you have in the model. And that is always the case, regardless of model type. It's not only for ANOVA, this is for regression or any other modeling. The STAT340 Rhapsody.
Is this the real life?
Yeah, okay. Rhapsody is a mixture of all kinds of styles, right? And I think that STAT340 is a little bit like this. We have seen many topics, many different methods and approaches, and we haven't really dug into any of them very deeply. So as a sort of concluding remarks here, how should we look up to the skies and see the real life? Let me say some few words about that. First of all, p-values. I know this is sort of a topics of some controversy. Some people hate p-values and say you shouldn't use p-values at all. I don't hate them. I use p-values, but you should at least know your null hypothesis. And that is something I have a feeling people don't always do. I see some scientific publications where p-values are listed, many of them. And I have a feeling that the author doesn't really know what he's testing. What does it mean, right? If you have a very small p-value, you reject some null hypothesis, right? But if you don't know what you're rejecting, then what's the point? You should at least know that. You should know more, right? But this is sort of the minimum, I would say. Also, please remember, effects may be significant, but irrelevant. If you have a lot of data or very precise data, even tiny little effects can become significant. But this doesn't mean that the effect is important. So please keep this in mind. Significance is a necessary but not sufficient requirement for something being of interest. It has to be significant, but it also has to be of some size to be relevant, I think. That's a good advice, I think, in all practical data analysis. First, significance, but then consider, is this really big enough to be important? So that's my about p-values. And then we are these days facing this artificial intelligence revolution. And that makes me think that whatever you do in life or when it comes to data analysis, don't become a robot. Because I also tend to see that people do data analysis as if it was a procedure. You just follow a sort of recipe, say exactly the same things every time, you compute exactly the same p-values every time, you don't really think, right? If that is what you do, then I would say a robot will do this much better than you. If this is all you can contribute with in life, you will be replaced by an artificial intelligence soon. So please be a little bit more than just a robot. Think. Get this under your skin. Don't just follow the recipe. Understand what you're doing. And finally, I think we have talked about sort of finding the truth in this course. What are the actual real effects, sort of the influencing variables and so on. One important requirement for finding the truth is that you are prepared to change your mind. And I think this is something that is worth remembering in our time, because it's not very popular to change your mind in these days. But if you are going to find the truth, If you're not going to ever change your mind about anything, you are in a bad situation for finding the truth. Then you have to stumble across it in the first attempt. Otherwise, you will never find it. So changing your mind should be something we should embrace more, I think. Okay,